Okay, this is going to cover types of phase changes. Most of this should be a review, but since we're dealing with heat, and heat basically determines what phase we're in, we need to go back over it again. So remember, these are physical changes. If we take ice and we melt it into water, it's still H2O. So nothing chemically has happened. So these are physical changes. Vaporization, remember, from a liquid to a vapor. Remember, if we're going up on our arrow, that's going to be an endothermic reaction. You're going to have to know those again, so make sure we review those. Up arrows are endothermic. Condensation would be vapor to a liquid. Melting is a solid to a liquid. Freezing is liquid to a solid. Sublimation is a solid to a vapor. And deposition, vapor to solid. I'll leave it up for a second. But you've got to pay attention to those endothermics and exothermics. They actually matter a lot here in just a little bit. We'll go back over the definitions when we get there. So make sure you know that the arrow going up is endothermic, arrows going down is exothermic. Be ready to recreate this chart like we did when we went over it. Now, phase diagrams. This shows you all the phase changes that can happen, along with the temperatures and the pressures that they will happen at. And you have one of these for every single compound that we can think of. So how to read this, there's three main parts. But first, you got to realize that everything is in equilibrium. This is another term from biology, where one phase change is occurring at an equal rate to the opposite phase change. So if I've got, for instance, this is December, we just had that ice storm. At 32 degrees, just as much ice was freezing as was melting. That's why I didn't see a whole lot of difference in the morning, because nothing really changed. It's all going at the same time. Then you get the normal boiling point. It's a boiling point that occurs at 1 atmosphere. Make sure you know this value so you know where to look at the chart. That's typically 100 degrees Celsius for water, but we're probably not going to give you the phase diagram for water on a test or a quiz. And the normal melting point is, again, where it melts at 1 atmosphere of pressure. So always look for that. It's 0 degrees Celsius for water. Then the triple point, which you can see on the graph, is right here in the middle. It's labeled there for you. Is the point in which all three states of matter coexist together. So I'll show you this little YouTube video down here if I can get to it. Alright, so let's get into how you actually read this. Sample of CO2, this is the phase diagram of CO2, has a temperature of negative 100 degrees Celsius. So you find the temperature down here at the bottom. Negative 100 is right here. And a pressure of 100 atmospheres. So 100 atmospheres would be right here. What state is the sample in? So you just match them up. Go up, and you meet it right there. And if it's the top left, it's a solid. You're going to need to know which part of the phase diagram is solid, liquid, gas. Solids are on the left, gases are on the bottom, liquids are on the top right. So it's going to be the top left. So that's going to be a solid. So if you take the sample from part A, decrease the pressure to 1 atmosphere, or 0.01 atmospheres, which will be right here, what phase change has been made? So if we match this up, that right there is going to be a gas. So we went from solid to gas, which is going to be sublimation. That's going to be dry ice for you. And finally, if you take the sample from part A and decrease the temperature to negative 200, so went from negative 20, increase the temperature to negative 20. So we're up here. Here's our original pressure. So at that point, we're in the liquid phase. What phase change has been made? Well, we go from solid to liquid. And that's going to be melting. Pay close attention to where it's asking for the state or the phase change in those questions. They can be kind of tricky if you're not reading the questions all the way. Now this diagram is a heating and cooling curve. These you got to pay really close attention to. Make sure you really know what's going on with the kinetic and the potential energy between the heats and the intermolecular forces. So you have diagonal lines. Those indicate the heating or the cooling of one phase. And this is big right here. You see it starred. Let's star it and box it. During the diagonal lines, kinetic energy is changing. So you see how this diagonal line going from on the solid part right here. Those are intermolecular forces being broken and formed. So those molecules are starting to move faster and faster. Eventually they will break into a liquid. That's why we say kinetic energy is only changing. And the horizontal lines, which I'll circle right here in green, only the potential energies can be changed. Sorry, I had a brain fart. The potential energy, remember, if you look at the y-axis, that's temperature. You can see how no temperature is changing right there. If no temperature is changing, that means it's in equilibrium, just as much as freezing as is melting. So no kinetic energy is actually being changed. Only the physical, or only the potential energy is going to change. And from here, you can determine the boiling and melting points. You have numbers over here in the temperature. So this right here, let me erase that. You just find the freezing point, come over here, there would be a number right here. Boiling point, you just drag it over here, and there would be a number right there for you to find those boiling and melting points. If you get that statement over there on the left, thermal heat energy is the type of kinetic energy. Kinetic energy does not change during a phase change. Third time you've seen it, third time you've heard it. It's important. It's going to be on your test and on your quiz. All right, so now let's go ahead and label this one. You got the chart in your note. It's already been labeled, so this shouldn't be too difficult. So you get your solid, liquid, gas first. Solids at the bottom, liquids in the middle, and gases are up top. You can see the separation of those molecules. Then boiling would be from a liquid to a gas. Remember, that's more scientifically called vaporization. Then melting would be from a solid to a liquid. Pay attention to what arrow you're putting that on. Freezing is going to be from a solid to or from liquid to a solid. Condensation from a gas to a liquid. And then temperature is going to be on the y-axis. And time will be on the bottom. Most of the time it's more like heat energy. But assuming we're heated as a solid, it's going to end up as a gas. So do phase changes occur on the diagonal sections or the flat sections? Well, we can see our freezing and melting, those are phase changes, so it's going to be on the horizontal. So what happens to the temperature of molecules during a phase change? No change. There's no kinetic energy change during a phase change. Describe how the kinetic energy of the molecules changes during a phase change. This is the same question we just asked. Remember, this is temperature, which is a form of kinetic energy. So you can see that that line is flat, which means there's no change in temperature, so again, we have no change. And finally, describe how the potential energy changes during a phase change. It's going to increase potential energy as we come down to more solids. So it's going to increase, going down, and decrease going up. But remember, we're talking about intermolecular forces. Solids are going to have a lot more intermolecular forces than gases. That's all we got.